Hello everyone. Today I'll talk about implicit under-parameterization inhibits data-efficient deep reinforcement learning. And this is joint work with Rishabh Agarwal, Dibya, Ghosh and Sergey Levine at UC Berkeley, Google and Mila. Modern deep RL algorithms typically have the following form. They employ a replay buffer that stores all the past historical experience that has been collected by the agent. And then they perform some sort of off-policy learning to train deep neural network controllers on top of this replay buffer. Some of the most popular off-policy deep RL algorithms are based on training a Q function or an actual value function, which is trained using some sort of consistency objective on the Bellman equation. In this work, we are interested in Q-learning algorithms that alternate between two steps. First, they would train Q functions by minimizing temporal difference error, which is basically the difference between the two sides of the Bellman equation. And second, they would collect new data in the environment by rolling out the resulting learned policy. Now, in contrast to this textbook style algorithm shown on the slide, we typically approximate this learning procedure by only solving step 1 for a fixed number of gradient update steps. So we do not solve this minimization problem exactly. We only solve it approximately using gradient descent. In this work, we are interested in broadly exploring the question of how this approximation to the optimization procedure, especially when employed with deep neural networks, affects the learning dynamics of such off-policy deep RL algorithms. In particular, we are interested in the data-efficient deep reinforcement learning setting, which is basically the setting where we want to be able to learn the most per unit amount of experience or data collected by the agent. So we want to be able to make the most number of gradient updates to our Q function on this data which is collected by the agent. In a supervised learning setting, obtaining data efficiencies is generally possible, and we have done that. In particular, we have algorithms that can typically get about 100 to 200 updates per data point. And these algorithms use very simple tricks. For example, they would control for some sort of statistical overfitting, or they would make sure that they could do early stopping. They would apply some regularizers during training, etc. But in the reinforcement learning setting, training even more than one step or one gradient update per data point can lead to poor performance. For example, this is a learning curve of the Sequest domain, which is an Atari game. And here, the red curve corresponds to one update per data point. The blue curve corresponds to 4 updates per data point, and the orange curve corresponds to 8 updates per data point. And you clearly see that even making even more than one update is generally very bad, because here the performance is super low, and it's low by a factor of about 4 in certain cases. Now, we may wonder if this is just due to, let's say, statistical overfitting, as we also see in supervised learning, and maybe correcting for statistical overfitting can be good enough in this case. But turns out that if we look at the training error, or the TD error, which is the training loss for the DQN agent in this case, we find that the training error is even higher with larger values of n. So it's not really statistical overfitting, because we are not even able to minimize the training error when we take more gradient updates. So in this work, we more specifically ask the question of why do we see this underfitting behavior when we train more, and why is it very different from supervised learning in this case? So in this work, we identify a phenomenon that we call implicit under-parameterization in deep Q-learning algorithms that is one of the causes behind the inability to take many more gradient updates on the same dataset in a deep Q-learning setting. So what we show here is that when we utilize some sort of temporal difference error, which utilizes bootstrap targets, that is target values for regression that are generated using the previous instance of the same Q function approximator, alongside a deep neural network Q function with the gradient descent optimizer to minimize this objective, what essentially happens is that a big Q network, a high capacity, highly expressive Q network, implicitly behaves as a low capacity under-parameterized network. So even if our Q function, our Q network had a lot of capacity, it was an extremely wide, extremely deep network, it would end up behaving as if it were an under-parameterized low capacity network which cannot even generalize correctly. And this phenomenon is what we call implicit under-parameterization, because this under-parameterization effect is implicitly caused as a result of training with such bootstrap TD error objectives along with the gradient descent optimizer. To formalize what implicit under-parameterization means and to quantify the degree of implicit under-parameterization, we come up with a new metric that quantifies the amount of under-parameterization effect that we see here. So assuming that the Q function is represented as a neural network that maps the state action pairs passes input to a feature vector phi, and then a linear layer, which is denoted as W transpose on top of this learned feature, we can define the effective rank of this feature matrix phi. So what we are doing here is we are taking a bunch of state action pairs as input, passing them through the Q function network, taking the last but one layer output of the Q function network, and calling the output tensor at that layer as our feature matrix, which is denoted as phi in the equations on the slide. And then what we are doing is we are computing the singular value decomposition of phi and measuring some sort of effective rank of this matrix phi using the singular value decomposition. This notion of effective rank is almost like the rank of the feature matrix, but in a sense it's a soft notion of rank. And what we talk about in this paper is that a low value of effective rank generally implies more aliasing, and the reason behind this is that when you have low rank, the Q function or the Q network is implicitly mapping all the state action pairs into a smaller dimensional subspace, which means it's coupling the values together at different state action pairs as inputs, and that means more aliasing. And we also argue that this more aliasing can lead to then poor performance. So how does implicit under-parameterization phenomenon happen in practice? So what we found with our experiments is that the effective rank of the Q function features decreases and eventually collapses when we do more training with a bootstrapped objective. In particular, when we do, let's say, in an online RL scenario, when we hope to be data efficient, as in we are taking more than one gradient update per data point, we find that the effective rank of the feature matrix generally degrades due to training. And when more updates are performed per unit data, this degradation is faster than when less updates are performed. In the more extreme case of offline RL, where we have a fixed data set given to us and we are not allowed to collect any more data from the environment, and we are supposed to only make updates on this data, we find that this rank or this notion of effective rank can even collapse a lot. For example, it can drop from about 400 to even 100 on the asterisk domain. And these drops and collapse in rank are accompanied by poor performance as well, as you see on these in these plots on the slide, indicating that rank collapse does actually strongly correspond to poor performance in this scenario. Okay, so next we'll talk about what are the causes behind implicit under-parameterization. And to answer this question, we performed a series of controlled experiments that I'll discuss next. So first, we observed that rank only decreases and collapses when bootstrapping is used. So if we avoid using bootstrapping, for example, when using Monte Carlo returns for training the Q function, rank does not decrease. Second, we ran an experiment where we reinitialize the Q function periodically during training. And what this reinitialization gives us is that it removes the effect of the moving nature of objectives on the Q function training. And even after removing this issue, we did find that rank does collapse, indicating that there's something really to the fact that the objective uses the previous Q function and that is one of the primary causes behind the rank collapse issue. Third, we also tried training Q functions using Oracle target Q values, which were generated by running tabular policy evaluation for the current policy pi. And in this case, we surprisingly found that the rank does actually increase and not decrease during training. So to summarize the key takeaways from this slide, we find that implicit under-parameterization or rank collapse does not happen without bootstrapping. And it's not just due to the fact that the objective for training the Q function is moving, like any other online learning scenario, but there's something really specific to bootstrapping that causes it. And third, when you use Oracle target Q values, it does not lead to rank collapse. Okay, so now we'll understand what causes implicit under-parameterization from a theoretical perspective. So our theoretical analysis is based off of this observation that in a supervised learning scenario, gradient descent leads to low rank solutions. So gradient descent has an affinity towards regularizing the parameter x to be of low rank, which technically implies that the larger singular values of x grow disproportionately as fast as compared to the smaller singular values of x. And so the larger singular values of x would end up becoming too large by the end of training. And we show that this rank decrease effect, which happens in supervised learning due to gradient descent, gets compounded due to bootstrapping, as shown in the schematic here, where when you utilize the previous Q function to generate the targets for training the current Q function, you are essentially incurring a rank drop due to the supervised learning reasons. And by using the current Q function as the target for the next Q function, you're propagating this rank drop over the iterations of bootstrapping. We have many more theoretical results in the paper, but I'll only discuss one of these results very briefly for this talk. So these results show that the ratio of singular values, where sigma I is a smaller singular value than sigma j, it generally decreases over time, in that sigma I by sigma j at time t is smaller than sigma I by sigma j at some time less than t, plus a very minimal bounded increase term that goes down to zero as more training is performed. We also have more theoretical results, especially when analyzing this phenomenon in the kernel regression regime as well as with deep linear networks in the paper that I'll encourage you to check out. Okay, so we finally discuss how we can potentially fix the rank collapse issue in deep Q-learning algorithms. So first of all, we talk about how exactly rank collapse might be hurting Q-learning. So we performed a control study on a grid world domain where we found that rank collapse essentially inhibits the ability of the learned features to represent the optimal Q function, which indicates that if you have a Q network that suffered from rank collapse, we might never be able to converge to the optimal Q function if we started training from that Q network. Now, to fix the rank collapse issue, we came up with a very simple fix, which essentially amounts to adding an extra regularizer on the singular values to the training objective of the Q function. And this regularizer, what it does here is that it penalizes the maximum singular value of the feature matrix or the learned feature matrix phi and pushes up the minimum singular value of the learned feature matrix. So what it's doing here is that it's penalizing the disproportionate increase in singular values, which is the result of more training and bootstrapping. And by applying this simple regularizer on top of offline RL problems where you have to learn from a static data set without any data collection, we find that this penalty improves performance on top of both a DQN algorithm as well as an offline RL algorithm, conservative Q-learning or CQL. We also apply this penalty on the the state-of-the-art rainbow algorithm in the data-efficient online RL setting, where we wanted to take 4 gradient steps per transition, and we found that even there, this penalty improved the performance of the base rainbow algorithm, as you see on the slide. Okay, to summarize, in this paper we talked about how Q-learning algorithms are not data efficient, and taking multiple gradient update steps per unit amount of experience can lead to poor performance. We talked about how bootstrapped updates in a Q-learning scenario can lead to feature rank collapse, which we called implicit under-parameterization of the Q network. And more concretely, this feature rank collapse is a result of the rank decrease effect that happens in supervised learning, compounding over time due to bootstrapped objectives. And fixing rank collapse can improve the performance in both offline RL settings as well as in data-efficient online RL settings, which makes it an interesting avenue to explore more. Thank you for listening.